My name is Ryo Yoshida from Meteorological Satellite Center of JMA. Thank you very much for attending this session. And I'm currently in charge of Himawari 8 cloud product in this center. Before Himawari 8 became operational, I had been responsible for software development for Himawari 8, image navigation and registration on the ground system. And this is the fourth year for me since I started work for Himawari 8. Okay. This is a picture observed by Himawari 8 on the 7th July this year. As you may know, Himawari 8 began its operation on this day, and this is the first imagery from when operation was started. One of the features of Himawari 8 is that it has many observation spectral bands. Especially, it has 3 observation bands in visible region, so that we can make true color image like this picture. The purpose of my presentation is offering an introduction of Himawari 8 in order to support the usage of its imagery. And these are the contents of my presentation. I've divided my presentation into the following 3 parts. First, I'd like to talk about overview of Himawari 8. And then, I will talk about data access such as HimawariCloud and HimawariCast service, including introduction of subtail service. And I will also introduce Imagery service on Meteorological Satellite Center website. Finally, I will show you operational information of Himawari 8, such as scheduled observation outage. Especially, Himawari 8 observation is affected by eclipse. So I will talk about these effects with image quality assessment. Now, I start to talk about overview of Himawari 8. The left top picture is outside drawing of Himawari 8. Himawari 8 is characterized by its optical imager called AHI. AHI stands for Advanced Himawari Imager. The great improvement of the observational function is brought by this optical imager. AHI class imager will be flown on many next-generation satellites, such as GOES-R series satellite by United States and GeoCompSat 2A by Korea. Among those satellites, Himawari 8 geostationary position is around 14 east degree. It is 3-axis attitude controlled geostationary satellite. And we have 3 types of telecommunication between satellite and the ground system. The first is low observation data transmission using Ka band. The second one is DCS. DCS collects some observation data such as tide level data or surface meteorological data by Himawari 8 from the place where cable connection is difficult. Those data are disseminated by GTS from JMA. The third one is telemetry and commands that are necessary for satellite operation. As for past and future schedule of Himawari 8 and 9 operation, Himawari 8 was launched on October in last year and began operation 7th July, as I mentioned, replacing previous MTSat-2 satellite. And Himawari 8 and Himawari 9 are identical in their function. I mean, it means Himawari 9 will also carry AHI. We plan to launch Himawari 9 next year. And it will be on orbit standby satellite for backup in case of significant trouble of Himawari 8. In 2022, we will replace operational satellite for Himawari 9. And geostationary satellite observation of JMA will be performed by those two satellites over long term, 14 years till 2029, actually. And Himawari 8 has a remarkable advantage in spatial, spectral, temporal, and flexible observation function over MTSAT2. As for spatial resolution, MTSAT 1R and 2 have 1 km resolution for visible band and 4 km resolution for infrared band. On the other hand, Himawari 8 has 0.5 km or 1 km resolution for visible band. As for temporal resolution, MTSAT 1R and 2 took 30 minutes for full disk observation, but Himawari 8 and 9 take only 10 minutes for full disk observation. And spectral capability is also improved. MTSAT have 1 visible band, no near-infrared band, and 4 infrared band. They have totally 5 bands. On the other hand, Himawari 8 has 3 visible band, 3 near-infrared band, and 10 infrared band. They have totally 16 bands. And finally, AHI can form more flexible observation. In MTSAT observation, in order to perform more frequent observation, it was required that special observation by standby satellite. This was called rapid scan observation. It was performed by MTSAT 1R when MTSAT 2 was operational. But Himawari 8 can always observe variable region every 2.5 minutes. In Himawari 8 observation, this regional observation is called target area observation. I show each advantage specifically in the following slide. First is spatial resolution. These pictures show the spatial resolution difference between MTSAT2 and Himawari 8. Those two data were observed at the same time. The left picture is visible band of MTSAT2, and right is MTSAT Himawari 8 band 3. Comparing MTSAT to Himawari 8 can clearly detect shape of cloud, this area, and surface condition, like surface condition pattern like mountain area and rivers and coastline are also observed clearly by Himawari 8. Next is about observation area and frequency. AHI observes 4 areas for meteorological imagery. They are full disk and region 1 and region 2 and region 3. Full disk, which is a whole Earth scene as observed the satellite. It is observed every 10 minutes by AHI. That is 3 times more frequent than MTSAT2 imager. Region 1 and Region 2 is Japan and its vicinity area. Performed 2.5 minutes. And Region 3 is target observation area. Observation area of Region 3 is variable by the commands from the ground system. JMA target typhoons and volcanoes by this regional observation. The following 4 slides are all animations of those observations. First is AHI scan. I hope that the movie works well for everyone. And this animation is AHI scan sequence in each 10-minute time period. AHI observe the Earth imagery with east to west continuous scans and north to south step. And full disk is observed by 23 scans. In addition to those full disk scans, you can see HI, Japan target area observed between full disk scans. In addition to those scans, you can see HI scanning some coastline areas. Japan area. And these two coastline areas performed. Those coastline data are used for imagery navigation collection on ground system. This frequent and complex scanning capability enables AHI to perform frequent and flexible observation. Next is temporal resolution for full disk observation. Okay. These two full disk images were observed at the same time by MTSAT-2 and Himawari-8. Both observations are visible bands, so only daytime area is available. As you see, Himawari-8 observes every 10 minutes. It is 3 times more frequent than MTSAT-2. Therefore, cloud movement and development are observed in detail, and the animation is very smoothly, we can see. This is an example target area observation for volcano. The eruption of Mount Silveti in Kamchatka Peninsula was observed. You can see volcano ash is being spouted and flowing to the south. Target area is variable in AHI field of view, and its interval is every 2.5 minutes. The range of target area observation is 10 kilometers square. Which area HI observes depends on the command from the ground system. And final animation is typhoon. This is some example typhoon observation observed by target area. Okay. As you see, observation area is moving gradually with following the typhoon course. That is, we prepare the observation area command based on the typhoon course prediction by our forecast division. As you see, target area observation offers more temporally resolved imagery than full disk one. Now I am going back the slide. Here I introduce characteristics of AHI 16 spectral bands. As I mentioned, AHI is the imager on Himawari 8 and 9. From band 1 to band 3, those are visible bands. Their wavelengths are in blue, green, red, so we can obtain true color image from these 3 visible bands. From band 4 to 6, those are near-infrared bands. Those near-infrared bands are effective for vegetation detection, ice water discrimination, and cloud particle size estimation. And band 7 is correspond to IR4 of MTSAT, which is used for lower cloud detection and hotspot detection. From band 8 to band 10, those are water vapor channel. Each band has a different sensitivity for the altitude. The longer wavelength band has sensitivity for the lower altitude water vapor. Band 11 and 12 are effective for detecting sulfur dioxide and ozone respectively. From band 13 to band 15, they are atmospheric window channel. Finally, band 16 has a sensitivity for carbon dioxide. Okay. This is a picture of RGB composite images from Himawari 8. This is an advantage of multiple spectral bands. RGB composite imagery can be displayed by 3 individual visual colorized images of 2 or 3 bands by composing them. With this RGB technique, interpretation of multiple band imagery becomes far easier. And Himawari 8 observation improvement also enhances not only satellite imagery, but also level 2 physical product, such as cloud product and AMVs and CSRs and aerosol and volcanic ashes. These products are expected to contribute numerical weather prediction, severe weather monitoring, and environmental monitoring. Session 7 on this Thursday will specifically introduce RGB techniques and level 2 products specifically by Mr. Hayashi from Meteorological Satellite Center. He is my colleague. And the improved observation brings increased amount of data. This bar graph shows data amount of Himawari 3 satellite from GSM-1 to MTSat. And the y-axis that shows data amount is scaled as GMS1 is unit. The amount of data was increased apparently between GMS and MTSat. This was caused by additional 1 infrared band and spatial resolution improvement. It would be possible to call this first generation alternation. This graph is the same with previous one, but with Himawari 8. There is a huge increase in between Himawari 8 and the others. It indicates that data amount of Himawari 8 is approximately 400 times bigger than GSM-1 and 50 times bigger than MTSat-2. This amount of data would be baseline of next generation satellite. And now I'd like to move on to the next topic, data access. As I showed, Himawari 8 has a huge amount of data. In order to distribute those big data, JMA constructed multiple types of distribution method. This table shows major data distribution methods, 3 methods. They are HimawariCloud, HimawariCast, and JMA WIS service. And HimawariCloud service is data distribution by Internet Cloud service. It provides the whole dataset of Himawari 8 observation. It's in HSD file format. It provides all the observation area and spectral bands with the finest spatial resolution. This is a service for advanced usage of NMHS. It is a National Meteorological Hydrological Services. Since a huge amount of data is distributed, high-speed internet environment is required for users. And HimawariCast. HimawariCast service is data distribution by a communication satellite. HimawariCast dataset is somewhat restrictive so that a wide range of users can access and can handle it. It offers full disk and 14 bands data with moderated spatial resolution. The amount of data is, the format of data is HRIT, which is the same with MTSat data. And it is open to everyone. In addition to those 2 major services, JMA provides Himawari 8 data through JMA WIS service. And it is characterized by SAT8 format. I'm going to talk about this service and SAT in the later slide. This is a schematic diagram of HimawariCloud and HimawariCast service. HimawariCast service is a way by a communication satellite. And in addition to HRIT files, it disseminates LRIT files and SAT files. To use HimawariCast service, you need C-band antenna and other receiving system. And HimawariCloud service is a way using Internet Cloud. It disseminates full data in HSD file. And net CD files for regional observation and PNG file for true color image are also available by this cloud service. And this chart shows the timeline of, In HimawariCast and HimawariCloud service, the full disk data are divided into 10 segments like those figures. First segment, second segment, then, and final 10 segment. So users can obtain full disk image after the last segment is acquired. This segment division is important to understand understand the latency of data distribution by those two services. This chart is somewhat a little bit difficult, but this chart shows the timeline of HimawariCloud data distribution. And horizontal axis means time elapsation. The raw data observed during every hour 5 minutes to the hour are distributed MFC about 2 minutes later. This point. And raw data, then after 4 minutes later, HSD data are created in MSC and started transferred to HimawariCloud vendor. It takes 4 minutes. And then those data are ready to pull by users. After all, the first segment is ready to pull within 7 minutes after observation start time. And the last segment is ready within 4 to 5 minutes after observation end time. This point. And this chart is the same with previous one, but for HimawariCast. The difference between HimawariCloud is the third and fourth step, which uplink to the communication satellite and downlink to the users. The first segment is to be disseminated to user within 8 minutes after observation start time. This point. The last segment is to be disseminated within 7 minutes after observation end time. This point. Okay. And this table shows a list of data disseminated by HimawariCast service. Full disk data of Himawari 8 are distributed in HRIT and LRIT files. The specifications of HRIT are as I mentioned earlier. And LRIT files are further restricted than HRIT. The number of bands is limited to 4. And the spatial resolution is 5 km. In addition to those imagery, numerical weather prediction data, in-situ observation data, and ASCAT ocean surface wind data are available in SAT format. And NWP data are 48-hour prediction data by JMA operational global model. In-situ observation data consists SYNOP, TEMP, and SIP. ASCAT surface wind data derived from metropolar orbiting satellites. In addition to those observation data, Himawari 8 operational those multiple data for their meteorological analysis. And JMA prepared so-called SAT software so that users can take advantage of those multiple data. SAT is a sophisticated display software visualizing meteorological information in multiple dimensions, and which assists forecasters to analyze and monitor weather parameters and phenomena for better meteorological services. And to tell the truth, this is a quotation from SAT manual, but I strongly believe it. And JMA has been offering SAT services for NMHSS within the framework of WMO information system called WIS. And you can access this website, and there are SAT data and its applications as well as useful information about these services. Himawari 8 data are also available on this WIS service. And this table shows specifications of dataset offered by WIS SAT8 service. As I mentioned earlier, Himawari 8 data are available through these services. It offers 4 bands, 1 visible and 3 infrared bands, with another meteorological data. NWP of JMA global model, and SST, SYNOP, and SIP, METER, TEMP, and ASCAT ocean surface wind data. And METER is aviation routine weather report data, and TEMP is upper observation data by radio zone. And dataset of those 6 areas, 1, 2, 3, 4, 5, 6, those 6 areas are available in this WIS service. And we go back to HimawariCast service. HimawariCast can assist weather monitoring and analysis with SAT software since it is designed to be suitable to the SAT software. That is, although the format of HimawariCast satellite imagery is HRIT as I mentioned, it can be converted to SAT format. And JMA prepared software also support this conversion. And the latest SAT software, version 3.0, supports all 16 bands of Himawari 8. And HimawariCast meteorological data can be also displayed in SAT software. So you can handle all the HimawariCast dataset by this SAT software. And this is another topic, dissemination by UMetCast of Himawari 8 data. Himawari 8 HRIT files have been available at UMetCast since October. And those are 11 band and 2 kilometer resolution. Courtesy of UMetSat, it became possible to distribute Himawari 8 data to the area where the HimawariCast satellite cannot cover. And another topic, this is an Imagery service on MSC website. MSC website provides JPEG imagery for Asia and Oceania region. It provides imagery for Australia, Central Asia, Pacific Island, and more. This is easy way to access to Himawari 8 imagery on near real-time basis with animation in the last 24 hours. Please visit this link. The specific areas of this service are described in the slide. Images for 19 regions are available actually. For several Asia regions, high-resolution images are provided with reduced area. These areas, and we are planning to add other high-resolution areas. And this service offers not only normal observation imagery, but also various RGB composite imageries, and totally 15 type imagery are available on the site. 15 type of observation. And in addition to those imageries, so-called heavy rain potential area product is also available on the site. This product provides information about the possibility of heavy rainfall associated with deep convective cloud. Those rainfall potential areas are identified by detecting convective cloud using 3 infrared bands of Himawari 8. And this product is produced for those 2 areas, Southeast Asia and South Pacific Islands. And final topic of data access part is data services provided to Japanese science group. These science group have started Himawari 8 distribution services on a voluntary basis for non-profit R&D users. And now, NICT is a National Institute for Information and Communication Technology. NICT and JAXA have started English services. And especially NICT services are multiple languages. It is interesting. So please visit 2 websites. This is JAXA's website called Himawari Monitor. They prepare Himawari 8 data monitoring page. On this page, you can monitor Himawari 8 imagery and level 2 product that is derived by JAXA. With registration, you can obtain Himawari 8 historical data. Since JMA data services are limited to near real-time data distribution, this service is very useful for historical data acquisition. Okay, the final part of my presentation is about Himawari 8 operational information. First is outage of observation. Himawari 8 has scheduled observation outage due to satellite events. One full disk observation is cancelled due to the satellite event in the table. First is maneuvers. Maneuvers which are station keeping orbit control are performed on alternate Monday, Thursday, and Friday. Although the time of maneuver is not fixed, they are not performed at every hour on the hour and half hour, because the observation on its time is very important. And unloading, that is momentary release from spacecraft attitude control wheels. It performed by twice a day at 2:15 and 14:50. During those operations, full disk observation is not performed. Finally, solar calibration. It is solar diffuse observation for AHI visible and near-infrared bands calibration. It is performed approximately once every 2 weeks instead of full disk observation. And schedule of those observation outage is available at this link. This is a link on MSC website. Next, I'd like to talk about the effect of the eclipse for Himawari 8 operation. Here, the term of eclipse means that Himawari 8 is in Earth's shadow. Please take a look at left figures. When it is summer or winter, they are not eclipse period. The sun does not enter AHI field of view like this figure. AHI is out of Himawari AHI field of view. Contrary, when it is spring and autumn, it is eclipse period. The satellite and the sun and the earth are located on the straight line at midnight like left figure. In this case, the sun enters AHI field of view and there is a risk of sunlight directly entering AHI optical system. In addition to this risk, significant thermal variation of satellite is caused when the satellite enters and leaves the Earth's shadow. These affect Himawari 8 operation and its imagery quality. And eclipse occurs from late February to mid-April and from late August to middle October. The affected time is about an hour, around 14 UTC. And next slide is effects of eclipse. HI has a function to skip a part of observation so that it does not scan across the sun for protecting its optical system. This is an automatic function called bright object avoidance, called BOA. When observation is partially skipped like those two figures, and this is skipped by HI. Although MTSAT2 cancelled the whole observation during the eclipse period, Himawari 8 is able to continue observation even during the eclipse period. This is another eclipse effect called stray light. It is image degradation caused by sun illumination of AHI optical system, but no root cause is identified. These examples are true color image at midnight on 13th April. You can see stray light here and here. There are no significant operational products from visible band at this night time. But unfortunately, not only visible band, but also shorter infrared bands, band 7 and band 8 are affected by this stray light. Those are band 7 stray light examples at midnight on 10th February. You can see darker areas which have higher brightness temperatures than usual. Here and here. And we found several cabling increase in brightness temperature observed. Thus, it requires certain care when you use those affected data. The next topic is image navigation quality. And the landmark analysis, which is pattern matching method between observed data and map. This figure shows the result of and yellow circle are landmark point and blue arrow are navigation error vectors. It indicates magnitude of error vector is very small. it mostly less than 0.3 pixels. This is 0.6 kilometer at sub-satellite point. Thus, we can say navigation quality is kept well. But we know that a larger navigation error occasionally occurs due to two causes. One is orbital parameter renewal in ground system. Orbital parameters for image processing on ground system are replaced from predicted one to measured one every day. Usually those two data are connected smoothly, but discontinuity occurs after maneuver operation. And this discontinuity causes several kilometers or several pixels navigation error, like left figure. But this orbital parameter renewal is performed when unloading operation. So only regional observations are affected, like this figure. There is no full disk observation. And the other navigation error is due to eclipse effect. And it occurs midnight during eclipse period when it often occurs with HI BOA function like left figure, like right figure. And the error magnitude of this effect is about 1 pixel, usually. And please keep in mind that the vector in those figures are exaggerated to be looked at well. Actual magnitude of the vector is within several kilometers, as I mentioned. And calibration performance is also validated, and which is radiation measurement accuracy. This slide shows infrared band validation with GSICS inter-calibration method. And left figure shows radiance 1-to-1 comparison of band 13 between Himawari 8 and ERG hyperspectral sounder on METOP. Both of two observations agree very well. And right figure shows brightness temperature biases between those two satellites, Himawari 8 and METOP, for all infrared bands. Those biases are very small and they are within 0.2 Kelvin. And next is validation of visible and near-infrared bands. Those validation is performed by comparison with radiative transfer simulation by Arster and Beer's observation result. Beer's is equipped on Suomi NPP satellite by NOAA. This bar graph shows the reflectivity ratio of HI to Beers and HI to Arster. The ratio to Beers is in blue, and the ratio to Arster is in red. The top figure is the result during April to May, and the bottom is in June. Result in June agree better than April. It means the value is close to 1. The ratio is 1. And since the calibration table were updated based on the solar diffuse observation in June. So this result and previous slide result show calibration quality for HI all band is kept well. So far, I have been talked the operational information for Himawari 8, and those information such as Himawari 8 operation status and calibration and navigation status, and including the information on eclipse effect are all available on MSC website. please visit this link. And for example, this is the contents of Himawari 8 operational status information on MSC web. You can get comprehensive information on this website. Okay, this is final slide. I'd like to summarize my presentation. First, Himawari 8 observational function is greatly improved with AHI spatial, spectral, temporal, and flex advances. And multiple methods for data distribution are available so that various users can access data. And HimawariCast disseminates meteorological data as well as satellite imagery. And it assists weather monitoring and analysis with satellite software. Himawari 8 has scheduled observation outage, and its operational information is available on MSC website. Finally, AHI calibration and navigation performance is kept well, but it is occasionally degraded, especially during spring and autumn eclipse periods. Thank you for your kind attention. That's all. Thank you.